Okay, I will start the class now. Today I'm going to start module 3, lasers, and this is very important for the second internals. Okay, in the second internals, the module 3 is completely there. It contains lasers and optical fiber, and lasers will be done by me, and optical fiber is, I think, already started by Anandram sir. Okay, therefore, I have already shared the notes. Please concentrate in the class. I will tell what are the important questions, and those questions are most probable. Okay. At any point, if you are not able to listen me, please raise your hand or chat with me. Okay. I mean, please inform me somehow. I will start the class right now. Lasers. Actually, okay. Laser is the abbreviation of light amplification by stimulated emission of radiation. Here, concentrate at the words such as amplification, stimulated emission. These two words are very important, and you will come to know what is the meaning of that. Okay. I think you know what is the general meaning of amplification. Amplification means multiplying something, adding something, or making the small thing into a bigger object, right? And stimulated emission means emission which is done by the help of external aid. Okay, I will explain in detail as class proceeds forward. Before going into the details, I just want to sum up what is the main difference between a laser light and the normal light. Okay, this question will not be there in the examination. This is for your self-learning part. Okay, laser light is monochromatic, that is it can emit only one radiation. Okay, one wavelength or one frequency. It contains only one color, that's it. Okay, and whereas normal light is non-monochromatic. And the second important thing is laser is coherent. Coherent means all the rays coming out of the laser will be in same phase. Okay, you can see these curly things over here. These are the rays emitted by the laser source. All these rays are in same phase. Constant phase is maintained between them, and therefore wavelength, frequency, everything will be same. Okay, and whereas in non-coherent sources such as normal light, the light will be emitted in random directions with different phases. And the third one is collimated nature of laser light. Collimated means unidirectional nature. Laser will travel in single direction. Okay, this is the third important thing. Whereas in the normal light, the light will be emitted in entire space. Okay, and in the laser, the power density is very high. It is of the order of 10 power 9 watt per meter square. This is very huge amount of power emitted by the laser source. If I expose the skin or any tissues to the laser light for a long time, those tissues will heat up and there will be a permanent damage in the skin. Okay, and whereas normal light source will not have such high density of power. It will be around 10 watt per meter square, very small compared to the power of the laser light. That is why we don't use laser lights for daily purpose, right? Lasers are used for some special purpose only, and even though they have very high intensity, we are not going to illuminate our rooms with lasers. That is because of the power density of laser. Okay, and that's it. I think this is enough about the comparison between normal light and the laser light. Just observe it and forget about it. Let us move forward. I will start with the three important concepts from the point of view of examination. The first one is, I mean, the main question from the lasers is the explanation about induced absorption, stimulated emission, and spontaneous emission. Okay, in the examination they will ask you to write a note on all these three things: induced absorption, stimulated emission, and spontaneous emission. I will explain one by one. I will start with induced absorption. I hope you understand that whenever energy or photon falls on the atom, electron absorbs that energy and goes to the excited state. Okay, but if electron goes to the excited state, can I say that entire atom itself gained energy? I can say that. Okay, if electron in an atom gains energy, that means atom itself gains energy. Therefore, in the laser chapter, I will not go for electrons. I will instead go for the atoms. Okay, I will say atom will be in the ground state and atom will be in the excited state. It will be similar to what you call electron in the ground state and electron in the excited state. Instead of electron, I am using the atom itself. Okay, atoms are molecules also will be excited to the higher energy levels to obtain laser. Okay, therefore, to explain induced absorption, I will start with atom being in its ground state. Okay, atom is now in the ground state, and as soon as there is a incident photon, this atom absorbs that photon and goes to the excited state. Okay, and that excited state, okay, is represented by E2. You can see this diagram, or you can also observe this animation. You just see here, this blue dot is the atom in the ground state. When there is a radiation which falls on this atom, that atom absorbs that radiation and goes to the excited state. You can see. Okay, this is known as induced absorption. The word induced implies that the atom itself has not gone to the excited state. Instead, atom is made to go to the excited state by incidenting a photon. We are supplying some energy from the external source for excitation. Therefore, this is known as induced absorption. I hope you know that atoms or anything in the universe will not go to the excited state on their own. It requires some external source. Okay, and I can express this situation by this equation. You can see atom in the ground state plus photon will give us atom star. Atom star means excited atom. Okay, this is known as induced absorption. Please remember this thing. And the next thing is the concept of spontaneous emission. Okay, spontaneous emission means, you know that every object in the universe wants to be in the state of lowest energy. This excited atom now wants to come to the ground state. Okay, and on its own, we are not actually supplying any energy. This excited atom on its own now comes to the ground state. While coming back, it will emit a photon. Okay, this is known as spontaneous emission. Spontaneous emission means, once again, it is the natural tendency which actually takes the atom in the excited state to the ground state. Okay, I will summarize this with a animation. The atoms in the excited state comes back to the ground state, and while doing that, it will emit a photon. This is known as spontaneous emission. Just observe the word spontaneous on its own. Okay, I can represent the situation by a equation. You just see atom star, that is excited atom, comes back to the ground state by emitting a photon. Okay, now here you can see I have actually incident a photon initially, and that photon is absorbed, and now the same photon is emitted. Therefore, there is no addition of photon has been taken place. The number of photons is left constant. You can see that, right? One photon is absorbed, one photon is emitted. There is no amplification, and this spontaneous emission is not responsible for laser. Okay, in the laser itself, you should understand there is a light amplification. That means if I supply one incident photon, there must be at least two photons emitted. That is known as amplification. And clearly, spontaneous emission will not give us any lasering action. Okay, therefore, we have to go for something else known as stimulated emission. Okay, stimulated emission means the emission of radiation. Okay, stimulated emission means the emission of radiation by using a external photon. You can see this diagram. I have made this atom in the excited state come back to the ground state by incidenting a photon. Okay, the word stimulated is important here. Stimulated means it is actually man-made, a kind of artificial thing. We have supplied some energy to bring the atom in the excited state to the ground state. Therefore, it is known as stimulated emission. Otherwise, the atom will not come to the ground state. Okay, you can now get confused because every atom wants to come back to the ground state, right? That is the nature, and that actually corresponds to spontaneous emission. But there are some special excited states, sometimes known as metastable states, in which the atoms will not come to the ground state. Okay, they will left in the excited state for a comparatively long time. Okay, the atoms, I mean, therefore you should understand there are two types of excited states always available. One is ordinary excited state, another one is metastable state, which is a kind of extraordinary excited state. Okay, ordinary excited state is short lived. Any atom which goes to the ordinary excited state will spontaneously comes back to the ground state. But any atom which is excited to the metastable state will take slightly longer time to come back to the ground state. Okay, this concept of metastable state is very important in lasers. Okay, and I will explain how this is important later in the class. Okay, just try to understand there are two types of emission processes involved in the laser. One is, of course, spontaneous emission. Another one is stimulated emission or artificial kind of emission, where we incident a photon to the excited atom, and the atom absorbs that photon and comes back to the ground state, and it emits two photons. One is incident photon itself, and another one is a stimulated photon. Okay, thus I am supplying a single photon and I am getting two photons, right? And both these incident photon and stimulated photon will move in the same direction and they are coherent. Okay, this is known as light amplification. Incidenting one photon, getting back two photons. Okay, and in the animation I have shown this. You can see the atom when hit by a incident photon absorbs that photon and comes back to the ground state. Okay, by emitting not only one but two photons. This is known as light amplification. Okay, this is all about induced absorption, spontaneous emission, and stimulated emission. This will be asked for 5 to 6 marks in the examination. Try to practice them. I have already shared in the notes, not that difficult. I can summarize the stimulated emission using a equation. Atom star, that means excited atom plus photon, will give us atom in the ground state plus two photons. This is known as light amplification. Okay, now I will go to the the next important thing, that is Einstein coefficient. Okay, Einstein coefficient, in the main examination or in the internals, they will ask you to derive expression for energy density in terms of Einstein coefficient. Okay, I hope you have never heard the word Einstein coefficient till now. I will explain what it is. It is quite simple. You have to obtain the expression for energy density. Which energy density? The energy density that you are going to supply to the system for induced absorption and stimulated emission, right? For two purposes, you are actually supplying the energy for induced absorption and stimulated emission. Keep it in mind. Now you have to find out that energy density that you are supplying. Okay, you have to find out the expression for energy density, and that in terms of Einstein coefficient. Okay, this is a very, very important question. Please make a note. This will be there in the internals, I think. If I set the paper, it will be there. Don't forget it. Practice today itself. Now I will show how to derive it. Okay. Now let us consider two energy levels, E1 and E2. E1, of course, is the ground state, and E2 is the excited state. N1 is the number of atoms in the ground state, and N2 is the number of atoms in the excited state respectively. And U of nu is the incident energy density. Okay, nu is the frequency of incident photon. Again, I repeat, we require photon for induced absorption and stimulated emission. Okay, U nu is the energy density, energy incident on the laser material per unit time per unit area. That is the meaning of energy density. Okay, now if T is the temperature, that is a constant thing. Now there are three processes which are going to take place. Okay, and one more thing I wanted to share, the radiation whenever interacts with the material, that is interaction of matter with the radiation, gives three different phenomena. One is the induced absorption, another one is spontaneous emission, and third one is stimulated emission. Okay, this is the consequence of actually the interaction of radiation with the atom. Okay, let us go to the derivation. If U nu is the incident energy density, then there are three things which is going to take place. First one is the induced absorption. Again, you already know that the atom in the ground state will absorb this incident photon and will go to the excited state. Okay, this is the induced absorption. In terms of equation, can I write rate of absorption is directly proportional to the energy incident and number of atom in the ground state? Okay, can you observe? Is this possible? Can I write rate of absorption, that is number of photons absorbed per unit time, is directly proportional to number of atoms present in the ground state and the incident energy? If you are not able to understand, let me tell you in a different manner. Okay, this rate of absorption must depend on the number of atoms in the ground state. If there are no atoms in the ground state, there will be no absorption, right? Therefore, rate of absorption must be directly proportional to the number of atoms in the ground state. And the second thing is, if there is no energy incidenting on the system, there will be no absorption. Therefore, rate of absorption is directly proportional to energy density of the incident photon and number of atoms in the ground state. Okay, try to convince yourself. These are the two things. If one of them is not present there, there will be no absorption. Forget about the rate of absorption. Okay, now the constant of proportionality, I will call it as B12. This B12 is known as Einstein's coefficient. Okay, I am going to define three coefficients of Einstein, one for induced absorption and another for stimulated emission and one for spontaneous emission. Okay, here rate of absorption is directly proportional to energy density U nu and N1, that is number of atoms in the ground state, and the constant of proportionality I will call it as B12. This is the Einstein coefficient. Please remember this formula. Okay, I will call this equation as 1. The next thing which is going to happen is spontaneous emission. Whatever, whichever atom actually now excited to the excited state E2 will not stay there for a long time. Hence, these atoms will come back to the ground state by emitting a photon. Okay, this is known as spontaneous emission. And rate of spontaneous emission is directly proportional to number of atoms in the excited state, isn't it? This is known as N2. If there are no atoms in the excited state, there is no spontaneous emission. Okay, I hope it is very clear. Therefore, rate of spontaneous emission is equal to A21. A21 is the constant of proportionality. This is the second Einstein's coefficient into N2. Okay, rate of spontaneous emission is A21 into N2. Okay, that's it. And the third thing, or the final thing which is going to happen is the stimulated emission. Okay, as soon as I incident the energy, there will be a emission of radiation, or the atom in the excited state now comes back to the ground state by emitting 2 photons. Okay, this is known as stimulated emission. Again, this stimulated emission is directly proportional to number of atoms in the excited state and the energy density which is incidenting. It is again obvious. If I am not supplying any energy, there will be no stimulated emission. Therefore, U nu should be there. And similarly, if there are no atoms in the excited state, there will be no stimulated emission. Okay. Now the constant of proportionality, I will call it as B21. Okay, this is the third Einstein coefficient. Okay, now there are three equations, one for rate of induced absorption and one for rate of spontaneous emission, and the third equation is for rate of stimulated emission. And it is quite obvious that rate of absorption must be equal to rate of spontaneous emission plus rate of stimulated emission, isn't it? That is because number of photons absorbed by the system must be equal to number of photons emitted by the system per second. Okay, therefore rate of absorption should be equal to rate of spontaneous emission and rate of stimulated emission. Okay, now uh, substitute the value of rate of absorption, rate of spontaneous emission, and rate of stimulated emission. You will see, you can see here, if I substitute all of them, okay, can you see this? Please raise your hand. Can you see from equation 1, 2, 3? Okay, thank you, I got it. Okay, now okay, am I audible now? Am I audible? Please, someone raise hand. Okay, okay, thank you. Okay, thank you. I think I am audible. Now I will start the class. Okay, Einstein coefficient. I mean, in the previous slide, you have seen that rate of absorption is equal to rate of spontaneous emission plus rate of stimulated emission. This is obvious thing. Now, if I write them in the equation form, you will see rate of absorption is equal to rate of spontaneous emission plus rate of stimulated emission. Okay, try to remember all these equations. Okay, now here I have defined three different Einstein coefficients. B12 represents Einstein coefficient during induced absorption. A21 represents Einstein coefficient during spontaneous emission. B21 represents Einstein coefficient during stimulated emission. Okay, these are the things which I have already discussed. Now uh, I can rearrange them. Okay, I will take the terms containing U nu, that is energy density, isn't it? What is our aim? Our aim is to obtain expression for energy density, right? Take the terms having energy density U nu to the left hand side, okay, and you will get this kind of equation. I'm only doing the algebra, nothing new. Take U nu as common, you will get this. Okay, you just practice today itself, you will find it is very simple. Okay, and then energy density u nu can be written like this. Okay, I have taken this term to the denominator of the right hand side. Okay, now what I have done is I have taken B12 or B21 and N2 common in the denominator. Okay, if I take N2 common, I can actually cancel N2 in numerator as well as denominator, and I can get this type of equation. You just see, I have taken N2 and B21 common in the denominator. Okay, thus I can obtain equation 4. You have to practice this. This is not that difficult. Okay, here you should remember N1 is the number of atom in the ground state, N2 is the number of atoms in the excited state, right? Now I don't know these exact numbers, therefore I have to take the help of one equation given by Boltzmann. Okay, this is known as Boltzmann's law. Boltzmann has given the expression for N1 by N2, or you can actually split them into equation for N1 and equation for N2. This was actually given by Boltzmann. That is, number of atoms in the energy level 1 is equal to e power minus E1 by kT, and number of particles in the energy level 2, that is N2, is equal to e power minus E2 by kT. Okay, thus N1 by N2 will look like this, or I can write N1 by N2 as e power E2 minus E1 by kT. This thing is a new concept for you guys, therefore you have to remember this. There is no other way. Boltzmann law is actually derived for science students, and for you guys you have to remember this. N1 is equal to e power minus E1 by kT, N2 is equal to e power minus E2 by kT. Therefore N1 by N2 is equal to e power E2 minus E1 by kT. Okay, now what is the meaning of E2 minus E1? E2 minus E1 is the energy difference between energy level 1 and 2, right? That is nothing but the energy of the photon. According to Bohr's theory, E2 minus E1 should be equal to h nu, or energy of the photon which is emitted. Therefore, I can write N1 by N2 as e power h nu by kT. Okay, e power h nu by kT. Now substitute this N1 by N2 in the equation 4. Then, okay, if I substitute this N1 by N2 as e power h nu by kT, you will get this equation. Okay, and now you have to compare this equation 6, that is energy density expression, with Planck's radiation formula. I hope you remember that in module 2, quantum mechanics contains this Planck's radiation law. Okay, somehow you have to practice it if you don't remember. E nu, energy density emitted by a black body, is equal to 8 pi h nu cube divided by c cube into 1 over e power h nu by kT minus 1. Okay, this formula you have to remember, and you have to compare this 6th equation with equation 7, that is Planck's radiation formula. If you compare that, you can clearly observe, in the place of B1 2 by B21, there is only 1 here, right? This is the first comparison, and in the place of A21 by B21, you have 8 pi h nu cube by c cube, right? Write that thing, that's it. You get A21 by B21 as 8 pi h nu cube by c cube, and B12 by B21 as 1. Okay, therefore what does that mean? B12 must be equal to B21. Therefore I can reduce the number of Einstein coefficients. Initially I had 3 coefficients, now I have only 2 coefficients. Okay, in the equation 6, write B12 as equal to B21, therefore this part will be cancelled, and in the place of A21 by B21, just write A by B. Okay, this is the final expression for energy density in terms of Einstein's coefficient. U nu is equal to A divided by B into e power h nu by kT minus 1. Okay, this finishes the derivation. This is a very important derivation from the point of view of internals. Okay, therefore please practice it. If you practice today itself, you will understand in a better way. Thank you very much for participating in the class. I will stop the class right now. Can I take class at 12:35 also? Please write in the chat box. Can I take class at 12:35 also? So that we advance into the syllabus. Okay, Disha is saying yes. Is there someone else wants this class? No, sir. Abhishek is not happy. Meghraj says okay. Is there someone else who requires the class? The only intention is I want to finish this lasers very soon so that you have enough time to read for the second internals. That is my intention. Your wish, sir, Strujan. As if you don't want anything, right? You are okay with that. Okay, Strujan. Is there any other opposition? If you have any opposition, if you don't have, I will take the class at 12:35 also. Till now, I have not received any opposition. Only one person is not happy. Okay. Please attend the class at 12:35 also. I will take only 20 or 30-minute class. Okay, not more than that. So that we will be in line with other sections. We are actually running slower than other sections. Everybody is busy in writing their name. Don't have any opinion about the class. Okay, I will take class at 12:35. Okay, it will be a short class. Thank you very much for participating. Today I have discussed two important concepts. The 6 marks or 5 marks question on induced absorption, spontaneous emission and stimulated emission, and a 8 marks question on expression for energy density. Okay, incident energy density. Thank you very much. If you have not followed, please don't panic. I will take additional classes in the offline mode also. I am ready to take as many classes you want. Okay, thank you very much. Bye.